got your last assignments here. I kind of don't think I'm contagious anymore, but I think it's just, I don't want to be the one. I don't want it to be me, and I just want you to feel safe, so I fucking hate teaching in a mask.
Yeah.
It sucks. Can you hear me okay?
Oh, yeah.
I think if you're teaching at the 40 before.
You think? I don't know. We'd have to take a vote.
My whole family got sick and it avoided me, so.
Yeah, my wife amazingly did not get sick either. Unfortunately, she was out of town. I had to take care of myself all by myself. It sucked. It sucked being alone and sick. And we have a fucking zoo, you know? We've got the 2 pugs and a rabbit. And it's just, when you're sick, just doing anything is a lot. But if you get COVID, I highly recommend the Paxlovid antiviral. I think that helped a lot. And am I right in thinking you might have something for me? Okay. Yeah, I tested negative on Sunday. And I've been on the antiviral since then. Just fatigue, mostly. Thank you, sir. Thank you. Thank you, ma'am. Thank you, sir. Somebody's 10 in there. Somebody's 10. Okie doke. Anything y'all need to talk about? No? Cool. Yeah, there was, most of that went really well, the Bolzano wire stress, but then there was the one that looks like this. We have this sequence that goes. That one there. That one caused some issues in a few spots. People were finding subsequences converging to things that weren't in there. So a really common answer was that it was all of this. It is not all of that. So I saw Liv wrote this in a really interesting way, and I'll share it with you. You could think of this sequence. Let me see if I can get it right. And I don't think I've ever seen this. And maybe, did somebody else here do that? Did one of you all do what I'm doing here? No? You did this? Did you write this, Camila, like this kind of table form with the
No, I
images?
wrote it like with the arrows, but.
Okay.
I'm the same thing with.
So you can, let's see, how does this go? So it's 1 half, 1, wait.
And then back up to 1/2, 1/3.
And then, yeah, I'm just feeling like I guess like that. Wait, can I see your lacing? Oh, okay, you gotta go across the top here, okay. So like that, and then up that diagonal. So here, down, and then up, and then around, I don't know, I don't think your arrows are right now that I'm looking at them, because you go from 1/3 to 1/4 then. And we want to keep hitting the ones, right?
Yeah.
So I don't think we can come back this way, Camila. And I gotta look at Liv, she might not have that right either. I don't know, is there a way to weave these?
Was that the? There is, but it was like really weird.
Yeah.
It like skips. I don't know how to explain it actually.
So we go like that, and then we start here and do like that, and then maybe it's like these increasing spirals. This actually kind of works.
Is it this one?
Is it which one? Yes. Yeah. Like a 1, 1/2, 1. Maybe I'm thinking of what the sequence we had is different. What's the sequence in the book actually? I think,
That's not,
I'm sorry, I screwed it, yeah, I screwed it up. I saw what was going on there though.
is that 11.10 that you're trying to look at? Or-
Yeah, 11, 10. Hey, look.
Hi.
Let me take a look here. Grab this, because I got something to give back to Liv anyway, so. Yeah, I don't think, and so Liv, we're talking about this one here. Oh, thank you, yeah, thank you. This one here, you and Camila both were talking, I was like, that's a cool way to look at it, but I don't think it gets us our sequence. Let me look at our sequence really quick. Because our sequence, oh, that's the fucking sequence they give us, isn't it? Okay. I don't know where in my brain I was thinking, somehow I was thinking it was this. Is this an actual problem somewhere?
Yeah, that was the sequence of 1.10 or 11.10.
Yeah. Wait. But it's not as given in the book, actually.
Oh.
That's the problem. I thought I saw a list like this. Did anybody ever see that list, or did I just?
Well, I mean, if we're talking about 11.10,
Yeah.
then I had a list that was kind of like that. It repeats the ones again.
So in 110 it goes 1, 1/2, 1, 1, 1/2, 1/3. Then it goes a quarter, but then it goes back down 1/3, or back up, 1/3, 1. And then you just get these pairs of ones. And I think it just keeps going deeper into this so that the next one is, so I might have to actually, I still think the answer is not, well, let's talk about what the answer is not in a second. I don't think this actually changes what I was saying. And then we go to 1/5, and then 1/4, 1/3, 1/2, and then double ones again. Yeah, I think it goes something like that. Is this the one you actually wrote down, or?
It goes to 1/6, but close enough.
Oh, on the next pass?
Yeah, it like hits the even ones. for some
Oh,
reason.
thank you. Okay, cool. Okay. 6, and then back. Okay, cool. And then out to an 8 on the next. Okay. So on this one, if you look at that they put that table there to kind of give you a sense of how to look at different views, different slices of the sequence. So for example, here's a subsequence down this column. That's one of the subsequences, right? There's a subsequence in here that's always 1. I think everybody kind of got that one. What other subsequences are there? Think about slicing this infinite matrix in different ways, not the weird laced way. Half. So then there's another sequence that's constantly half, just right down this way, right? And that goes infinite. That's repeated infinitely times. And then there's a 3rd, and a 4th, and a 5th. So in a lot of folks' papers, a number of folks' papers, we don't have a lot of folks in general, many folks were claiming this. as all possible limits. But my question, I think, in each of those was, how do you get to 2/3? And how would you get to 2/3 using any of the subsequences here? And I don't think you can. So the set of limit points, the set of possible limits, which are called limit points, the possible sequences and where they converge to is not everything in here. And so that's something I've asked, I think, a few folks to think about. Definitely, and then actually, I think some folks got this, 0, 1, because there is this sequence that goes this way that does converge to 0. Absolutely, a lot of sequences and subsequences that go to 0 in there. But it's a weirder beast than you might think. Is there any questions on anything else you just got back? Like any comments or anything that don't make sense? I was in a COVID fugue, so maybe I didn't think properly. Yes, ma'am.
You said to explain why it goes to 0 on mine, so.
Yes, can I see which one we're talking about?
That same, this one.
Oh. Yes, so just show me.
So like,
Oh.
showing them like picture of it?
Well,
Or
just,
like,
um,
or
just
you want me to write it as a group?
as a subsequence. So just give me the subs, and you basically almost have it there, but you're showing that as the list of possible limits. So you have this there, Camila, and you've got 1/2, 1/3, blah, blah, blah. And you're saying this is the collection of all possible limits. But like, just explain what subsequence gets
Oh,
to each of those. Does that make sense? Just a little more detail. You got it right. Definitely. Another thing, notationally, the subsequence stuff, and this is a learning process. If there was one on there, this was another common one. Say I've got some subsequence, and then I have some other subsequence of that. So first off, try to use lowercase letters for sequences and real numbers. When you use, and Christian, I hope I didn't call you out, but you use capitals, and that's like culturally in math a matrix, which you could have, but luckily we don't have that here. So use lowercase in general. And when you're talking about a subsequence, get used to using this subnotation. Does this need a little explanation? Or do you understand how this works? Okay, so one of the problems it says, I've got a sequence that has a subsequence that is bounded. And then it asks you about a subsequence of that subsequence. The subsequence of that subsequence is going to be grabbing, so think about what this guy looks like. It's AN1, AN2, AN3. And these, we don't know what these are. And now we're gonna select a collection of these from this list. So if I were to select, for example, this one here as part of my sequence, I would put a little, so 1, that would be my first. And then if I selected one down here, somewhere down here, let's say I selected AN5, I would say that's AN5 sub 2. So I'm going to be putting an extra layer of subscript on here. So I'm going to grab the first n sub j, the second n sub j, the third n sub j, and so on. So when you go to the subsequence of a subsequence, you're going to have triple subscripts. So that's a weird thing to get used to, but I'd like you to practice that notation. So I probably send it back to you if you didn't do that, just for some quick tweaks. Any other questions? Good. All right, I'm kind of excited. I'm sorry we're having a smaller class today. I felt like it was better to have some kind of in-person class than to, I don't know, I'm feeling good enough to be out in public. But after I did that Calc 3 recording, I was dead. And I thought, oh shit, doing 3 classes in a row in person, dancing around up here, gonna kill me. So, trying to take it easy on myself so I don't get rebound COVID. Oh, excuse me a second. Oh boy, nice and toasty in here. Okay, very exciting digression. I'm gonna give you a different section of a different book to look at for this, but theoretically, the section we're going through right now is 13 in this book, but they go into higher dimensional space. So we're here, they present the chapter as this. I don't like that, and we don't need to go there to get the ideas that we need. We don't need to go to n-dimensional space. So essentially, what we got is we're going to study basic topology. This is cool shit. Like the first time I took a topology class, it was one of the coolest math classes I ever had. And I wished I would have had real analysis before it, because honestly, it's almost like abstracted real analysis. But you can also think of it as the study of the connectivity of things, of sets and things like that. It's weirder than that. You'll see. So let's get some basic definitions and then work with them. Basic definition 1. A set O, which is the subset, I'm going to make a fancy O like that so it doesn't look like a 0. Subset of the reals is open. Oh, one last quick definition. Define a delta ball around a point x naught. I'll draw the picture. Here's the real line. Here's the center. Here's x naught plus delta. Here's x naught minus delta. So it's this open interval right here, centered at x0 with a radius of x naught. So it's equal to this. And we could write that also as the set of all x such that x minus x naught is less than delta. And again, you want to be able to kind of go with all those definitions. So, and then I read that as a delta ball about x naught. And thinking in terms of these balls makes topology so much easier. They don't really introduce it in our book, which is unfortunate. So a set, some set collection of points in the real line is open if for all points inside the set. So I take a set, let's come over here. Let's draw the classic open set. Take a point in there, there's O. For every x that I take out of that set, there exists some delta that's positive, some distance, so that the delta ball around x naught is also contained in the set. Right, that's as good as I'll write shit fast and then come drink tea. So it's a very odd definition. You ever seen anything? Have you ever seen this definition before anywhere? I didn't think so. That's why it's really important that we cover it. It's a very different way of thinking. And we're about to move into the study of continuity of functions, and understanding some of this is going to make that all richer, much richer and stranger as well, which makes it better. Always. Strange math is always better. So let's do some examples real quick. Let's say, I'm not going to say this is O because I don't know that it's open. Let's just say, is the set open? We'll start with our first one. What do you think? I mean, I know what you think. I know what you would call that thing. How would you say this? How would you read this, just in your mind? AB. How would you talk about the endpoints?
Open interval from A.
You would probably, yeah, like you've probably called it the open interval from A to B before. Well, the reason it's open, now let's explore that. I'm going to take a point X inside here. X naught. How can I build a delta ball around X naught to ensure that it doesn't spill outside the set? So what I'm saying is this set is open because for every point inside it, we can find a delta ball around that X naught that is completely contained in the interval. How would you build it here? And let's assume the picture's kind of drawn true, that the X naught's closer to the A. How would you build? What would you let delta be to make sure that your delta ball didn't spill out of there?
Less than the absolute value of A minus X naught?
Yeah, you take a look, and I feel like you were going to say that, Liv. I don't know, I felt like you were going to say that. So yeah, you look at this, you look at the place that X naught is closest to, either the A or the B, and then just set your radius equal to that, right? So here, if X naught is, and we're going to do this in a more elegant way, closer to A, then we're going to let delta equal. We can also see that X naught is to the right of A. It's inside that interval. So this is a positive quantity because X naught's bigger than A already. And if you were worried about this, you could just go, you know what, I don't like being that close, I'll take half of it. And then your delta ball doesn't even come close to the end. So what we could do is to account for the fact that X naught could be in the middle or it could be closer to B, we could let D equal the minimum distance between X naught and A and X naught and B. So if this was the min, we have the situation that we're in right now. It means X naught's closer to A. If this is the min, it means we're closer to the right side. Gets us covered. And then just let delta equal 1/2 that distance. So it's always taking half the distance. That way if X naught is over here, I'm just going to take half that distance, and there's my little delta ball in there. Remember, it says ball, but it's really an interval for us. It's a little open interval. So that would be the way to make it tight and not have to worry about cases and stuff like that. But one thing to keep in mind is that this delta depends on the point, right? And when we look at the definition, it's saying there's a call and response for every point in here. This should say X naught right here. For every point in here, there exists a corresponding delta. So you might even want to make a note that delta will probably depend on the point you choose. But you can always find it. So let's take a look at some other examples. I'll leave that definition. Is it okay if I erase here? Appreciate you, cool. Camila, good. Courtney, good. Okay. Alright, so how about this one? Should take a minute, think about that. I can see a smile on Courtney's face. You might know. But like, see if you can come up with the argument for the thing you're thinking. And the only answers here at the point we're at now are open or not open. We don't talk about closed. Not open doesn't mean closed. I need to draw this stuff out. And you gotta kind of go through with your mind. See if you can find a trouble spot. Is there some point in there where no delta ball around that point can fall completely inside? Is there a trouble spot? What do you think, Christian?
I'm thinking, yeah, because like you could do like the A, I guess.
Yeah, looks pretty bad, right?
Yeah, then there wouldn't be a delta ball unless like delta is 0.
Yeah, and we don't get that. Delta ball's always thick. It's always got thickness. So that's one of the cool things about open sets. They have thickness. There's always like a solidity to them. So right here, if I pick any ball around that, half of it will fall in, but the left half will fall out. No matter how tiny I try to make it, no matter how small that delta is, this left side is going to be out of the interval. That is the only point in there that has that trouble. If I scoot just a little bit to the right, I'm back at the situation we had in the last example. I can just make sure it doesn't go past A. So this one is not open because any delta ball around the point A, with delta positive, of course, spills out to values less than A. So, does it make some sense? Okay, let's do some other examples. Open. Not getting enough sleep, Camila?
I've gotten too much sleep probably.
Oh, seriously?
Problem.
I hope you're not getting sick.
I don't think so.
Okay, that's good. That's good.
Yeah, no. My whole family's gotten sick. Everyone around me has gotten sick, and then except for me. So.
Got some nice genetics there.
Yeah.
Nice.
Yeah, my mom last night she was like, "Oh, I'm not feeling well." And my sister and my brother were sick over the weekend, and I was just like, "Oh."
There goes another one.
Yeah, and my sister and I share a room, so I feel like I would have gotten sick by now.
Absolutely. Yeah. Hope they've been being kind of like keeping it out of your faces. If you don't, like I didn't wear a mask in our house, right? I'm just like laying in bed with Amy, you know. Just poisoning. Is this open? Real line? What do we think? What do you think, Liv?
Yeah.
Yeah, agreed. Can you give me a quick argument?
I guess like no matter where you go, it isn't. There's no way to like be out.
Yeah,
There's no like
perfect. Yeah.
boundaries. Or,
Make delta as big as you want. You're good to go. Any delta ball around any point is in the set. That's, yes, so beautiful. So no matter how hard you try, you cannot leave the real line. So the whole set is open because for any x naught that's real, any delta ball around x naught is contained in there. That's a big ass space. All right, I'm gonna give you this one because this one's kind of hard. The empty set is open. So the empty set is open is a hard thing to see until we talk about the relationship between open and closed. And that's not as obvious as it might seem. The empty set is open because the definition of open is, I'm going to write this out, vacuously satisfied. By the empty set. Has anybody seen that before? Vacuously satisfied? Yeah. So this is a very fancy ass logician mathy thing to say. So if I said to you, every unicorn has 2 livers. There's no way, we cannot determine the falsehood of that because there are, to our knowledge, unfortunately, no unicorns, right? Now that sucks, and I hope I'm wrong, I really do. But let me explain it in a different way. Every implication, so any implication, A implies B, is true in the case where A is false. You got, the way I mean by that is it's true in that weird ass logic table way, right? So we think about our logic table. Here's A implies B. Here's B. Here's A. Remember, this is a switch being flipped, right? This switch turns on that light. And if I end up in a possible scenario, it's true. If the scenario is impossible, then it is false. So if this switch is flipped and that light is on, yeah, that makes sense. Of course, that switch controls that light. If this switch is on and that light is off, that ain't good because I know that this switch, I made that damn circuit. That switch controls that light. That is not a possible thing. However, if that switch is off and the light's off, well, yeah, that's what I pretty much planned for. But then there's that damn switch I don't know about that somehow turns on B that I'm not thinking about right now, but somebody rewired the house all weird ass. And so if my switch is off and the light is on, I can't say that can't happen because there might be other ways to turn the light on. So notice that when the hypothesis is false, the resulting implication is always true. This is vacuously satisfied. And that's what we have here. We just don't have, we can't, we just have nothing satisfying the hypothesis, so it's true. So this is just a thing to remember for now, and I think on Monday it'll probably make a little more sense. All right, one more example here. I guess that's called the naturals. Open or close? Oh, not close, just open. Open or not open, sorry. You think you know, Camila? What are you thinking?
I think it's not open, because if you pick one, you're out from the left side.
No matter, and the right side, right?
Yeah.
Yeah, so if you take any of these points in the real line, so here's the real line, here's my set, it's discrete points. Blah, blah, blah. Pick any one of those as your x naught, and immediately there's literally no delta ball that doesn't spill outside the set, so absolutely. So this set is not open. Good work. What about the complement of that set? Do you know what I mean by that? Everything except that set. Is that open? Let's take a look. Okay, I'm gonna redraw it. Christian, you're giving me a pretty firm no. So here's the set I'm thinking of. It's the real line sans those points. So tell me why you're thinking not open. Now you're starting to think that maybe you were too hasty, I
Yeah, I
think.
think I might have been a little bit too hasty.
Yeah. So why?
So I was thinking about like negative numbers, and I was thinking more so about like, I guess like you would flip the natural like numbers over and just have negative. I was gonna say.
Oh.
Yeah.
Yeah.
You have like 0, and it'd be like the same sort of idea.
Yeah. But that's not exactly what, so now you see, it's
Yeah.
literally just take the naturals out. So these are just little open intervals. And this is an infinite open interval. And no matter where I pick, this just comes back to this one. Between 1 and 2, 1 and 2 is not included. If that 1 were included, I'm still okay. Because it's the kind of infinite amount of space this way. But here, you can always find little ones in there. And way over here, you can make them even bigger. So the complement is open. Okay, so let's see. Let's get a couple properties of open sets. And I hinted at one just right there. So properties of open sets. I'm going to introduce a very interesting notation that we haven't used this semester yet. Suppose that big O sub alpha, where alpha is an element of some big set A. So also big capitals also indicate sets, I guess, not just matrices, as I said just a minute ago. So this is called an indexing set. And this is, instead of, your normal indices, the ones you're used to are 1, 2, 3, 4, 5, when we have sequences, first element, second element. But you can talk about collections of things that are uncountable. So for example, I could have the collection of all -1 plus x, or let's write it, x minus 1, comma, x plus 1, open interval, such that x is a real number. That, like literally over every single real number, I put this interval of length 2. That's a shitload of intervals. That's a lot. And a lot of over-covering. But this will become important because at some point we're going to cover things with sets and then uncover them in certain ways. And this is good that we see this now. So suppose is a collection of open sets. So everything in there is an open set, has the property of the delta ball stuff. Then the union of any sub-collection. So I'm going to take alpha out of B, where B is a subset of the indices O sub alpha. So this is an arbitrary union. This could be something like this. So over here, for example, I could talk about the union of all these guys here, where x is equal to an integer. So that's a subset of the original the original index set is everything. Here I'm saying just grab some of the indices, but there's still infinitely many. Here. So here we're grabbing a subset, and this is open. And the best way to think about this is with this phrase: arbitrary unions of open sets are open. We're not going to prove that today, but I think we might do that on Monday. We're definitely not going to do much else today. And I want to get one important fact in here before we go. Finite intersections of open sets are open. Notice the play and the difference. Let me let you finish getting that up there. One last little example I'll show you before we call it for today, because it is a short class today. I said, and this stuff's kind of heavy. I'll definitely give you some stuff to look at over the weekend. I just got to get it together. Arbitrary. We'll get back into this on Monday. Arbitrary intersections may not be open. And there was a set I gave, I was having a discussion with Cormac and Christian early in the semester about an example. Consider this example. this look like? And maybe Liv, were you involved in this too? I can't remember, but, that just goes on and on forever. What is that intersection? It's just zero. The only thing in there is zero. You're basically taking intervals around zero and shrinking them in. And the only thing that can be in here is the singleton zero. Are single points open? No, because right when they have a terrible, zero is not open because every delta ball falls outside of it. So this is not open. But as long as you only have a finite number of open sets where they can't shrink to zero size, that's what's killing it. The ability, once you have infinitely many things, they can shrink down to nothing and give you single points. Yes, sir.
That still just may not be open. It is possible for them to be
It
open.
is possible. So yes, because if I took the inner, shit, I gotta think. It's not a definite though, but I have to think better than I'm thinking right now. That's a great question. I'll get on that. All right, that's it for today, my friends. Thanks for being here.